By all the standard laws of physics and probability, an ultra-large crude carrier crossing the ocean should end its journey as a fireball. These leviathans stretch longer than 3 football fields and carry up to 2 million barrels of raw petroleum. In financial terms, that is roughly $150 million worth of cargo locked inside a single steel hull. Unrefined petroleum is highly volatile, constantly emitting flammable hydrocarbon vapors. Transporting it means securing a massive, sloshing payload of combustible energy through violent ocean storms and unpredictable currents. The reason these ships reach port intact is that they operate as heavily armored fortresses. Every pipe, valve, and bulkhead is specifically engineered to counteract the exact physical forces trying to tear the vessel apart. To understand how a modern oil tanker works, you have to look at how maritime engineers manage to keep a 600,000-ton floating bomb from detonating. The first major threat is a physical phenomenon known as the free surface effect. If you've carried a wide baking pan filled with water, you know how the liquid violently surges back and forth with every step. If an oil tanker carried its cargo in one giant hold, millions of gallons of heavy crude would surge together. When the ship rolls, that massive wall of liquid slams into the hull, driving the center of gravity past the tipping point and forcing a capsize. This diagram shows tanker layouts from Panamax to VLCC. The space is partitioned into a grid of smaller compartments. By breaking the hold into center and wing tanks, the liquid's lateral momentum is restricted. It cannot build enough kinetic energy to threaten the hull. Slicing the cargo into these smaller sections allows the ship to use internal geometry to lock its center of gravity in place, remaining stable even when the ocean is completely chaotic. Stability solves the tumbling problem, but there is still the chemical threat. As a cargo tank empties during a voyage or while unloading, the newly created empty space fills with highly combustible hydrocarbon vapors, mixing with atmospheric oxygen. Normal atmospheric air is about 21% oxygen. For those trapped hydrocarbon vapors to ignite, the oxygen level needs to remain above 11%. If that concentration drops below 8%, combustion becomes physically impossible. To force that oxygen level down, tankers rely on the inert gas system, or IGS. This system actively pushes an oxygen-deficient gas mixture into the cargo tanks to replace the breathable air. Instead of generating this gas from scratch, the ship harvests its own exhaust. The toxic fumes generated by the ship's massive diesel engine are captured, cooled, scrubbed of impurities, and piped directly into the cargo holds. Because this exhaust gas is nearly devoid of oxygen, it acts as a suffocating blanket. Any stray spark caused by static electricity or metal friction inside that tank is instantly smothered. The engineering turns a waste product into a critical defense mechanism, surrounding the most flammable cargo on Earth with a permanent, fireproof shield. While the inert gas system neutralizes internal explosions, the ship still has to survive external impacts, like running aground on a hidden reef. This cross-section shows the mandated physical defense, the double hull. 2 distinct layers separate the cargo from the sea. That 2-meter gap acts as a water ballast tank and a sacrificial crumple zone. If a reef tears the outer steel, the inner tank remains intact. While crude oil tankers use massive, simple tanks for raw petroleum, refined product tankers carry gasoline, diesel, and kerosene simultaneously. To prevent cross-contamination, their decks are overlaid with complex, segregated piping networks and individually sealed compartments. The whole design works in both directions. It protects the fragile marine ecosystem from thousands of tons of toxic petroleum, while insulating a highly sensitive payload from the battering force of the ocean. Pumping the oil out at the destination creates a new mechanical problem. Crude oil is heavy and viscous. As the tank drains, it leaves behind a thick, clinging sludge coating the steel bulkheads. Clearing that residue with fresh water would require millions of gallons, generating a massive volume of highly toxic wastewater that ports cannot easily process or store. To bypass the water problem, engineers utilize crude oil washing, or COW. This diagram illustrates the cleaning machine, a submerged, rotating shaft equipped with a high-pressure nozzle mounted directly inside the cargo hold. Instead of water, the machine siphons pressurized crude oil from the cargo itself and blasts it against the walls. Under high pressure, crude oil acts as a powerful solvent, dissolving the clinging sludge so it pools at the bottom and can be pumped out. Using the cargo to clean the cargo tank is an elegant loop. It ensures the buyer receives maximum volume, leaves the steel relatively clean, and requires zero fresh water. When the ship is docked safely at a highly organized terminal tank farm, the cargo is transferred ashore through heavy robotic arms, concluding weeks of high-stakes navigation. That raw crude quickly moves into refineries, broken down into the gasoline that powers your car, the plastics in your phone, and the fuel that heats your home. The entire framework of modern commerce depends on thousands of these specialized vessels, constantly resolving massive physical and chemical threats in real time. The next time you pull up to a gas pump, remember the engineering to get it there. Your full tank is the final result of a 600,000-ton steel puzzle, fighting the ocean and winning.